Hello, I'm Maciej, and today I'll be talking about the not very overly represented topic on this conference, because it's artificial intelligence, but I'm glad that so many of you are here. So unless we met at our stand, you probably don't know us. So we are Silver Bullet Labs, and we are part of the QED software, and we're crazy about the AI. And here in Krakow, we are with Grail, which is our AI middleware for developers, for game dev companies, as well as Tactical Troops, which is our game that initially was planned as a test game, like a proof of concept for Grail, but it grew into a regular, fully fledged game. And apart from that, in QED, we're doing AI and machine learning-based solutions. So we're all over the place in this topic. And a very quick introduction about me. I'm also so crazy about the AI that I even did a PhD in this area. And I worked commercially both in Poland and in the lands down under. And to further back up our credibility, we developed a multiplayer bot for an RTS game, Ancestors Legacy. So if you know this game and if you play it against the AI, that's our solution too. So here's the plan, and basically the plan is simple. I'll be talking about the game and the challenges in this game because the title is Truly Complex AI, so I will say why we believe it's complex in this game. And I will introduce Grail and how these two are combined in one piece of software, in one solution. And of course, I will end with some conclusions. So what is Tactical Troops? It's a 2D game. Although you can see some shadows, but in a sense, it's a 2D game because units on the map have basically two coordinates, X and Y, and it's turn-based. But although it's turn-based, it's not on a grid, but the movement is continuous. Like you can see here, a circle that shows how far a unit can go. So each position inside the circle is possible for the unit to achieve. And we don't have any randomness in this game. Shooting and everything is based on physics. And we have a system of action points. So this inner circle, for instance, shows how much we can go and still use the currently selected action. The environment is dynamic, so it's important in terms of AI, that AI has to react to this dynamic environment, and we have teleportation technology, more to follow about this. And some games that are somewhat similar are Jagged Alliance or Worms. Some people said that Commandos also is a similar game to Tactical Troops. How to win in this game? We have 4 options: elimination, domination by controlling control points. These control points are shown here, 1 to 3, and capture the flag, and devastation. And the designers may use one or more those conditions. And essentially, multiplayer bots have to have them in mind too. So that's the victory conditions for the bots too. And from the AI point of view, another measure of complexity is how many actions are there, how many behaviors are there. So in this game, there are lots of actions because the movement is not on a grid. So movement, all the positions that troops may consider. Shooting, there are over 30 weapons. Reloading those weapons, the ammo runs out. And gadgets such as grenades, mines, cloaks, as you can see, shields, armor, and also Overwatch, which allows shooting in the opponent's turn. So that's really a lot of actions. I already mentioned the teleportation technology. Almost anything can be teleported. Not everything, sorry if you got offended. Units can go through teleporters. We can shoot through them, throw objects through teleporters, for example, grenades. If you played Tactical Troops, you can play it here at our stand. It's really nice to be killed by AI shooting a grenade over a teleport. I think it's very satisfying for an AI developer. So yeah, that's tough, basically, because it breaks the nav mesh, right? Teleportation makes the pathfinding more difficult, too. So to sum up, what are the challenges? There are natural challenges, such as balancing between victory conditions. There are 4 or even more of them, because designers may put more on a map. And coordination of units. We control a number of units, typically 4 or 5 or 6. So they need to coordinate. And also on a unit level, there are many actions to choose from. And what's the right weapon to attack with? There are lots of decisions to make. So that's why I think that the AI for this game is a complex system. How to approach this? We know what's the goal, but how to success? So if you think about the AI in a game, it typically techniques such as on the left-hand side are used, such as behavior trees, the most prominent one, I would say, or finite state machines, sometimes just simple scripts, or sometimes even nothing. Many games do not have advanced AI. And on the right-hand side, you can see I put some of the scientific methods, such as neural networks, support vector machines, or random forests, or other machine learning-based methods. And Grail is something in between. We want to use some scientific quality methods, but also we don't want to bring many problems that are related to them. So what are common fears when we think about those academic methods? So the common fears we hear actually from you and from AI developers, from game developers, that they are hard to design, that we don't really have much control over many of them. And it's important, right? Because we ship the game and we want to know what essentially, more or less, will happen. They can be too overpowered in a very non-human way. They can be ruthless, for example, and they can be unpredictable, of course. And usually, very successful applications of scientific AI has to run on a very powerful hardware. So they are combinational heavy, very heavy. So that's why we seek some middle grounds. And what's the Grail? Grail is an engine, a middleware for the AI, and it's from the top view, like bird's eye view. It's a multi-agent system where agents communicate between each other, and the communication is based on blackboards. But blackboards can hold any information. You probably heard blackboards, for example, from Unreal Engine blackboards. And one of the interesting features are shared blackboards, that entities may share blackboards with other entities, and it's quite easy to define which information is available to which entities. So we can model senses or memory just using a simple concept like blackboards. And also, Grail is a collection of AI techniques. That's the meat, I would say, of the AI, and I will be going over them. And finally, maybe you're interested how Grail can be used. The products are libraries, programming libraries for C++ and C#. And also, based on these libraries, we will ship plugins to perhaps the 2 most popular game engines out there. So this is just a quick excerpt from the architecture of Grail, and the central element is behavior, so like in behavior trees, what entities can do, and these behaviors can be instantiated. So you provide basically what's possible in the game. So you provide behaviors or templates for behaviors, like prototypes, and templates are similar to, for example, environmental queries in Unreal Engine, when we show what's the structure of behavior, but we don't specify concrete parameters, such as, for example, a behavior can be find a safe spot, and the actual safe spot, the coordinates of the safe spot may be parameters. And playing model is an algorithm of choosing the right behavior. So, and we can build hierarchy of playing models of entities that use playing models in a very free way as we want. We can build any hierarchical AI, and why it's important I will show in Tactical Troops. And this is quick peek because it's a programming track after all. So this is a quick peek how the code looks like. I think it's not very overly complex. It's a part of the behavior class, how it looks like, what's the style of this. Yeah, so let's move to the implementation of AI in Tactical Troops. So because there are natural challenges, like strategic challenges, tactical, and some local coordination, we defined a hierarchy of AIs using using Grail. And on a strategic level, of course, it's the top one. What AI does here is a rough global assessment of the situation. Basically, what's the situation in the game in relation to the victory conditions. Strategic level gives orders to the tactical level. And how we approach strategic level? We use the so-called utility system, and it's one of the 4 Grail techniques. I mentioned the AI techniques. It's one of the 4 we have. And utility system is based on utility curves. Utility curves are tools to define what affects the utility of a behavior. For example, on an x-axis, we have, for example, let's consider an example behavior, like finding a health medkit, for example. So on an x-axis, we have consideration, and the consideration may be how high is our health. On the y-axis, we have actual utility of finding the medkit based on the current health we have. And it's a simple tool to model relationships, and those relationships, for example, utility of a behavior may require more than one consideration. Those utility curves are combined together, and it gives like fuzzy logic quality. And we develop, with Grail, we ship a graphical tool to set this up in a graphical manner, so it's easier. And here we can define the utility curves. So we also have utility curves editor. And what are the benefits of utility system? It's relatively design friendly, and it's high performance, especially to compare to other methods we have. And this is a quote from Dave Mark from GDC conference, that utility system handles situational edge cases better than behavior trees, for example. So this is a technique, and I will show how we use this technique in Tactical Troops. And it was used, well, not this direction. Utility system has been used in some games, such as Guild Wars or The Sims, League of Legends, and XCOM. So it's not completely new. And we do it in two steps. First, we run some pre-processing, because we have those victory conditions, and some decisions can be chosen by algorithmically. So you don't need to focus on the actual numbers. What I want to say here, that first we do some pre-processing to find how the troops stand in relation to victory conditions, and we do it to answer 4 questions. Can we rush to victory, for example, by securing the control points? Can the enemy rush to victory, so uninterrupted, so we cannot do anything about it? And we check if we are expected to win quicker, for example, we are much closer to control points, or if an enemy is expected to win quicker. And based on this, we first run a heuristic to select which points of interest, and for example, capture points or flag, depending on the actual setup of the map, which points of interest are the most pertinent to go to. And we generate the so-called urgent orders, strategic orders for the units. And the utility system for this step is really, really simple. Units are chosen to go to those chosen points of interest based on their distance and their distance of other units to those selected points of interest. So sometimes we don't want to greedily choose the closest unit, but also we consider other units, so the global sum of distances is the lowest one, and it just translates to utility with some multiplication, because we want to give really high utility to those orders. So this is just the first step, preprocessing. We choose very important points of interest to go to, and some units will be assigned those points of interest. And also we have remaining orders. So orders are actions, behaviors on a strategic level, such as protecting another troop, or assaulting points of interest, or defending in, or just going on rampage, seek and destroy. And the utility system for those actions is also quite simple. So the utility system, in essence, is choose the action with the highest utility. So we do it like while there are units without an order, we repeat this process to assign an order to a unit, and each order have utility, and basically the utility is based on, first, how far is a unit from a particular order, for example, points of interest, or ally, or enemy, how good a unit is to make this order, to do it, how threatening is the point we are going to, and how we already mitigated those threats. So if the point is threatening, then we want to assign more utility, higher utility to this, and if we already assigned units there, we lower this utility. So we combine it by summing those utilities. So we sum basically 2 curves. And from distance and unit strength, we multiply it. And such a simple system, just setting 4 curves and merging them together, gives the final utility of an order. And while there are still units without order, we repeat this process, so we have orders for each unit. Okay, and now what happens? Or not. Now we have orders, and what happens next is something more, I think, more complex. So we use a tree search technique, actually that's coming from academia, and to make we play a simplified game within a game. So we generate a graph of possible positions for a troop, and you can see this graph is quite dense. And each node in a graph is a position, and those positions are either procedurally sampled, but also points of interest are always included there. Also units positions are included there. And edges are between each nodes that there is a line of sight, basically. So either units can go there or shoot through those units. And it handles teleports also. in a natural way, because we add artificial edges where teleports are. And once we have such a representation, we treat it like a board game, actually. So we use the so-called Monte Carlo tree search, which has got some attention because it was the algorithm of choice of Google DeepMind's AlphaGo system that won against probably the best player of recent several years in this game. And it was a huge breakthrough in science. And so we employ this technique in video game. This technique uses, for example, in comparison to traditional min-max search, this technique requires only a simulator of a game. There's no expert knowledge required, but the simulator must be fast. So that's why we simplify our game in order to be able to simulate it efficiently. And we can do around 10,000 simulations per 10 seconds, maybe, so 1,000 simulations per second, so around that. And this technique is iterative, so repeated many times, consists of 4 phases, and builds up a tree of memory where each tree represents a state in a game. And why it's Monte Carlo? Because the tree is built just one node after another node, one node per each iteration. And when we always start from the root node, so we start from the tree we already have, and when we fall out of the tree, we do random sampling until the end of the game and fetch the result, and just keep statistics of which moves were good or bad for each player. And what's become really a breakthrough is a smart formula. I won't go over it in a detail, but this formula tells which actions to choose here in this selection part of the tree in order to balance between the best actions found so far and the exploration of the space, so finding new actions, checking out new actions. So it's a very good formula for balancing exploitation and exploration. It does really work. It really works great in board games, but of course, video games are usually more complex. So, so that's one of the reasons. That's the only reason that's probably you haven't heard that much about this technique. So in this simplified game, I showed you the graph that units can move, and these are actions available to units in this simulated game. Moving a unit from one graph node to another graph node, using weapon on a graph node, using gadget such as shield, for example, or passing a turn, or activating Overwatch. So it's a bit simplified version of the game because it uses these graph nodes as possible positions. And I told you that this method doesn't really require expert knowledge and just simulates to the end of the game, but because the game is quite long, the units may stall or may go backwards, go around the map. We terminate the game earlier, so we simulate only to a certain horizon. So, for example, 1 turn, 2 turns, or 3 turns ahead. And when the simulation goes for example, 3 turns ahead, we just terminate it and return the evaluation of the current position for each player, how good the state is. And this evaluation is based on hit points of units, satisfaction of victory conditions other than hit points, so other than whether units are alive or not, and distances to targets chosen by the units, so to targets that the high strategic level orders ask the units to go to. So only 3 components actually, and they are summed together for each unit, and this is an assessment of a situation in a game, just 3 turns ahead. And we just keep crunching those simulations one after another and simulate the possible ways the games can unfold, and this method returns the best actions found so far. And also just to show how because I said that hit points evaluation, I just wanted to show how we do it, and not going into details, but showing how complex it is. I think it's not that complex. Just a few formulas that gives us the score, how good the situation is. Okay, so now I told you what are the orders of the strategic level, and here I included which of the evaluation function components are used with each order, and once we run the Monte Carlo tree search algorithm, we have orders from tactical level that are good, or we have evaluation of each order from tactical level. So we have the proposed action from tactical level for each unit. So first we have strategic level orders, then we have tactical level orders, and now we want to apply those orders actually. So just to sum up, the Monte Carlo tree search performs iterations, crunches them, and after chosen number of seconds, we have the results. For each action, we have the score of it. So we choose the highest score actions, and we put them into blackboards, and units take those written behaviors from blackboards and realize them, just execute them using atomic behaviors, for example, actual movement from one point to another, or actual shooting. And this diagram shows how it is combined. So 3 levels: strategic level, tactical level, and units. And strategic level has its own blackboard and writes to a shared blackboard with tactical level. Tactical level reads orders from strategic level and writes to run simulations, gets the results, and writes the recommended actions from tactical level to the blackboards of respective units, and units take those information. And there is also this local unit level that does pathfinding and simple avoidance, for example, not to shoot a friend which is on our side. And the unit will move, for example, 1 step right and shoot from there. And really, here is an option to overwrite an order if really some emergent local situation says so. Okay, and also on this level we use threat maps. On the left-hand side you can see threat maps, so basically where a unit can be shot or killed, and also mass map to avoid friends or push through boxes, because in this game units can also, some obstacles can be moved, so the unit may decide to go around or push through those obstacles. So this is not done by the AI. This is a simple heuristic using a mass map. Okay, and this system is quite easy to be equipped with difficulty adjustment, because I told about the utility system, so we can just tweak weights of the components of the utility system. We can multiply those curves by some weights in order to achieve a different behavior. So some of them will be stronger, some of them will be weaker. So we can do easily different settings of the utility system, and they can be used for difficulty adjustment. And also for the MCTS, because it's a method that's based on simulations, the more time we give to it, the better it becomes. So this is also a very simple way to adjust difficulty. Just stronger bots will have hard difficulty, will have more time to think, and easy may use less time. And if we don't want to make it noticeable, we can, of course, allow that the bot always will use, for example, 3 seconds, but only certain amount of those seconds will be used for simulations, if we really want to have them always act after 3 seconds, of course. Okay, so those two techniques were used in tactical troops, but we also have two more. So one of them is planner, and planner is it's a way to go from some starting state to some goal state, and compared, for example, behavior to finite state machines. Here we only model local interactions by means of precondition and post-conditions of action. So what's required to make an action and what an action produces. And only based on those local definitions, the bot will figure out the path to achieve a certain goal. Or it will answer that it's not possible. So it's a nice technique, for example, for crafting games, because the bot will find the proper chain to it. And you can see the crafting game at our stand. And for planners, we also have a graphical tool to assist to see the plans. What actions are chosen after what actions? What are the sequences? So each color is a different action. Planners were used in games such as Killzone, Fear, or Stalker. So they are not new, but they're not that popular in games yet. So we also, by including it in the Grail, we also think that they should gain more popularity because they're quite easy to design, and maybe not that efficient for very complex games. That's why we also have utility and MCTS. And the final technique is evolutionary algorithm. And for this technique, we don't really use it for action selections, but we include, in Grail, we included the so-called arena. What is arena? If we have a game that's based on fighting or interaction of bots, we can put them into arena to pit them against each other, and they will keep playing against each other in a repeated process, which is steered by evolutionary algorithm, and though the results of the fights between them are translated to fitness function of the genetic algorithm. So the new generations are stronger than the older generations, and this can be a lifelong learning optimization process. We can run it, for example, for night or for a week, and have lots of parameterization of bots. And that we can use them in various ways, actually. We can use them for difficulty adjustment also, for difficulty levels, because the final bots will be probably the hardest to beat. The initial ones will be the easiest to beat, and somewhere in the middle, there will be some middle difficulty bots, probably. So we can use certain bots for certain levels, or we can test the game this way. So it's a nice tool to optimize some parameters in the game. And to conclude, our vision at Silver Bullet Labs is for the next gen AI is to took the best of both worlds, actually, both scientific world and the commercial world. So we are aware that the algorithms needs to be quite easy to design, to control, to test, and really high performance. Because unfortunately, the AI usually has a small portion of the frame, actually. And from scientific world, we want to have more procedural approach, that we only define what's the game about, what are the goals, and the bots should figure out how to play. So in Grail, we use methods that are, I would say, somewhere in the middle, because both utility and MCTS and planners all of them are a little bit easier to design than behavior trees, and they scale better when the game grows, because they adapt to changes in a natural way. Yeah, and basically that's gonna be it for today. So if you have more questions, and probably you do, then you can contact either me or Mr. Piotr Biczyk using emails shown here. So thank you for your attention.
Okay, thank you very much. Any questions?
Yes?
Oh, yes. Okay.
Hello, you talked a bit about scaling. Can you elaborate a bit? Can it handle 1,000 units, 10,000 agents? How does it scale, your system?
Yeah, actually by scaling I meant that when the game world grows, or more things, for example, are added, or more actions are added to the game, more things should be considered for the AI, then those methods will adapt because they're built on basic principles. For example, the Monte Carlo tree search will only need you only need to add those actions to the simulation, and it will compute new scores, so it will adapt. So this is, I didn't mean by scaling by performance. I mean changing, when the game grows, the model of the game grows, then these methods usually do not require so much tweaking, because they already, the simulation part or the base is already there, so we only add new things. But performance-wise, I would say that we chosen methods of different performance. The utility system is really fast, and sampling curves can be really fast, can be really optimized, and it is fast. But for example, this Monte Carlo tree search is as fast as the simulator is, and it's usually not that fast, so it's recommended for either for turn-based games where there's some time to make a decision, or are recommended for strategic decision in games which do not have to be computed every frame, or for example 1 per minute, just to do some strategic level. I've heard, I'm not sure, but I've heard that the Monte Carlo tree search was used in the latest Total War games for the strategic part. Yeah.
Thank you.
Okay. Any questions? Okay.
Hi, thanks for the talk. I was wondering if you compared the Minimax algorithm with Monte Carlo one, and if there were any huge advantages.
Yeah. The advantages of Monte Carlo tree search are enormous. Basically, min-max-based search is pushed away from almost all its original applications, because min-max search first and foremost requires the evaluation function to work with, unless we can search through all possible states and all possible actions in the game till the end. That's the only case when evaluation function is not required for min-max. And I mean, game trees are huge. For example, in chess, you have more nodes than there are estimated atoms in the universe. So min-max is always used with evaluation function, and the tree with min-max grows exponentially. So in order to have more accurate assessment of situation, we need to add a whole layer in a tree. So it grows exponentially. And Monte Carlo tree search samples the space, maybe not that dense like min-max, but it chooses actions chooses better actions more often. So the tree in Monte Carlo tree search is really asymmetric. It's more dense where actions are better, more promising. And really, the results show for themselves in chess, in Go, in almost any domain where min-max was used. Monte Carlo research is better. It's beating it. So.
And in terms of computation time?
Yeah, it's also better, I would say, because min-max, well, it's hard to compare them because they differ in a way that min-max only traverses the tree and gets the evaluation function. Monte Carlo research traverses the tree to some point, falls out, and does random simulation of the game till the end. So it's hard to compare performance because the process is a bit different, but one of the advantages of MCTS is that it's very easy to parallelize because those simulations can run to a certain amount in parallel, so you can use as many computers as you want. It typically scales up to 30, 40 computers very, very well, typically, and then it slows down more. But yeah, and Monte Carlo research is also can be stopped in any time, and it will give the currently best action as it thinks. And min-max really, if you stop it in the middle of calculation, then you won't have probably better evaluation until a whole new level in a tree is added. So you have like these steps. So yeah, actually Monte Carlo research is in almost every way better.
Okay, thanks.
Anyone? Okay. Thank you very much.
Thank you.